On a une petite minute d'avance. Ok, on va. Okay, let's start. Okay, welcome to everybody. Well, so the last lecture was the crash course on algebraic groups. I can understand that it was lots of material to digest in a few days. So maybe you have questions about the last lecture before we go on. Other questions? No questions? Okay. So during the last lecture, we defined what we review some results, many results on algebraic groups, but these results were about algebraic groups defined over the algebraically closed field, in particular an algebraic closure of FP. And today we will introduce the notion of FQ structure on an algebraic group. And in fact, the notion of FQ structure is the same as for a variety, except that there is another structure on the algebraic group. So the definition of an FQ structure on an algebraic group is the following. An FQ structure on my fixed algebraic group G that I will assume to be linear, which means that the variety is affine. So an FQ structure on G is the datum of a Frobenius endomorphism F from G to G over FQ. So this is, for the moment, just the definition of an FQ structure on a variety. But since we are working with a group, we also require that F is a morphism of algebraic groups. So which is a morphism of groups. Of groups. Okay, and in this case, we said we are interested in the finite group GF, which is a group of elements in G, which are fixed under the Frobenius. And this can be viewed as FQ rational points in some model of G, which is the model is induced by. So of course, I need to give some examples. So example in dimension 0, when G is finite, this is just the datum of an automorphism of the finite group. This is nothing more. I must say that when you are given an FQ structure on G, so Frobenius endomorphism, which is a morphism of groups, we have seen that F is bijective as a map between sets. Okay, so F is in fact always an automorphism of groups, but it is not an automorphism of algebraic groups in general, if the dimension is bigger than or equal to 1. Because Frobenius is not an automorphism of varieties. Another example is the Frobenius on the additive group F plus that sends x to the q. And in this case, the group of fixed points is just the group of the additive group on FQ. Similarly, you have the same map that works over the multiplicative group, so F less than -0 endowed with a multiplication. And in this case, of course, the fixed point subgroup is FQ star. A somewhat more interesting example, if you take F from GLNF to GLNF, that sends the matrix to the same matrix where all the entries are raised to the q's power. Since raising to the q's power is an automorphism of the field F, this induces a morphism of groups. And in particular, in this case, the group of fixed point is just the general linear group over FQ. But this example can be somewhat improved. As follows, not improved, but twisted as follows. So if I denote by FU the map that goes from GLNF to GLNF, that sends a matrix to again the matrix where I raised the entries to the q's power, but now I use a non-trivial automorphism of GLN, so the transpose of the inverse. Okay, in this case, the square of FU is equal to the square of F. Okay, so we have seen that this implies that FU is also a Frobenius endomorphism. Over FQ. Okay, and in this case, what is the group of fixed point? Okay, under this Frobenius. In fact, it is the group denoted by UN of FQ square. This is a unitary group. And this is a unitary group because it is defined as follows. This is a set of G in GLN of FQ square. So this is because if you are fixed under FU, then you are fixed under FU square. So you are sure to belong to GLN of FQ square. But you must satisfy the following equality, that G times the transpose of F of G is equal to the identity matrix IN. Okay, so this is a unitary group. And why is it called a unitary group? Because by analogy with what happens with the complex number, here F is an order 2. F is an order 2 automorphism of the field FQ square. So this is the analog of the complex conjugacy over the complex number. And you recognize the definition of the unitary group in the complex setting, but you just change the field and the automorphism of order 2 you are working with. Okay, so this is an example of a final group you can obtain using this kind of constructions. A fourth example is to twist again the Frobenius, but I fix a Frobenius endomorphism of G. Over FQ. And I still denote by F the same automorphism of F to the N, of G to the N, and I define F prime. This is the map that goes from G to the N, from G to the N to G to the N, that sends an n-tuple of elements of G to the elements that I obtained by making a cyclic permutation, but I apply F to everybody. Okay. And in this case, F prime to the nth power of F is equal to the nth power of F prime is equal to the nth power of F, where I denote by F the endomorphism of G to the n, which is obtained just by product of the Frobenius endomorphism. And so again, because the power of F prime is the power of F, this implies that F prime is a Frobenius endomorphism. But what about the fixed point? In fact, the fixed point under F prime, it's an easy computation to see that it is isomorphic to the fixed point of F to the n on G. And the way it works, you send an element G to the element obtained by taking as a first coordinate G, then you apply G F to G, and so on, until F to the n minus 1 of G. And you can check that this is really an isomorphism of finite groups. Okay? So this is here an example where you can obtain G to the F to the n, which this group can be obtained from an FQ to the n structure on G, but it can be also obtained by an FQ structure on G to the n. This way of thinking can be useful. And the fifth example is the following. If you take G, an element of G, then if you twist an existing Frobenius by the action of G, so I define GF from G to G that sends H to first I apply F to H, but then I conjugate by the action of G. That's what I denote by GF. Okay. Then this endomorphism is also a Frobenius endomorphism over FQ. And I will leave this as an exercise. Okay. So I can start immediately with the main theorem of today. If you remember only one thing of this lecture, this is the following theorem, which is not very difficult, but very, 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 very useful. This is a Lang's theorem. So I fix, and until the end of this lecture, I fix a Frobenius endomorphism F on G over FQ. Okay. So I can define the notion of F conjugacy. How is it defined? So the formula G dot F, this is an action which is indexed by H. So the action of G, the dot F action of G on H is equal to G H F of G inverse. So this is a kind of conjugacy, but I twist the right-hand side by the action of my endomorphism. So this formula defines an action of G on itself. And this action is called the action by F conjugacy. And we denote by H1 of F and G the set of F conjugacy classes. Well, so this notation comes from non-abelian cohomology, but you don't have to care about. Just take it as a definition that H1 of F and G is a set of F conjugacy classes. And the theorem, the first theorem of today's lecture, is that if G is connected, then H1 of F and G is reduced to a single element, and the single element is the full set G. Okay, or in other words, this means that the Lang map, that the orbit of one is everybody. So this means that the Lang map, that I'll denote by L, that goes from G to G, and that sends G to. So if I take the action of G, I should write G times F of G inverse, but sometimes it's more convenient to take the action of G inverse. So I take the action of G, the dot F action of G inverse on 1. And so the theorem means that this map is surjective. Okay. So let's prove this very important theorem. So if A is in G, then the stabilizer of A for the dot F action, so I denote it like this, okay? This is the group G to the AF. This is a group of fixed points under the Frobenius endomorphism AF. This can easily be checked from the formula. So from the example here, AF is a Frobenius endomorphism. So this is really the group of fixed point under Frobenius endomorphism. So in particular, it is finite. So the orbit omega of A, so it has a dimension equal to the dimension on G minus the dimension of the stabilizer. Okay, so it has dimension. It has dimension, the dimension of G. Okay, but so since G is irreducible as a variety, connected, I recall that connected and irreducible are equivalent for algebraic groups. So since G is irreducible, this means that the closure of A is equal to the full group, okay? And I recall that an orbit under the action of a group is always open in its closure. So in fact, this implies that omega of A is open in G. Okay, so this was the proposition 5.13 in the last lecture. And in particular, the orbit of A is open. The orbit of 1 is also open. This is the same argument, of course. And two open subsets in an irreducible variety have a non-empty intersection. So it shows that A is in the same, when two orbits intersect, it means that they are equal. So it means that A is in the same orbit as 1. So in particular, since it is true for every A, this proves the theorem. So you see that the proof is very easy, but the consequences of this theorem are very, very, there are many, many consequences of this theorem. The first one is quite interesting, but there will be much more, much deeper consequences. So corollary 6.2 is that if you want to compute the set of F conjugacy classes on a general algebraic group, not necessarily connected, then in fact, you have only to compute the set of F conjugacy classes on the finite group obtained by the quotient of G by the connected component of the identity. Okay, so let's prove, and you will see how we can use Lang's theorem for proving this, a proof of this corollary. Okay, so the natural map there is a natural map. If you have an F conjugacy in G, you can send it to its image in G mod G0. And this will give you an F conjugacy, a union of F conjugacy classes. This will give you an F conjugacy class in G mod G0. And so the natural map is on 2. But the point is to prove that it is injective. So for this, let G and H be element of G, be such that they have the same, their image in G mod G0 are in the same conjugacy classes. So be such that there exists A in G and G0 in G0 such that the conjugate of H, the F conjugate of H is equal to G up to an element of G0, and this element is G0. Okay, so this means that the F conjugacy class of H and the F conjugacy class of G have the same image in G mod G0. Okay, but we want to prove that they are H. This implies that G and H and G are F conjugated, but by Lang's theorem, applied to the Frobenius endomorphism GF, G times F, the one that was defined here. Okay, there exists B in G0 such that, so I apply Lang's theorem to this Frobenius endomorphism, but also to G0, not to G. G is not connected, but G0 is connected. So there exists B in G0 such that B minus 1 G F of B times G inverse is equal to G0, because G0 is an element of this connected component. And in particular, you can check that an easy computation shows that this implies that AH F of A inverse is equal to B minus 1 G F of B. So this implies that H and G are in the same F conjugacy class. And I conclude this subsection with a remark which will be useless for our course, but it is for your mathematical culture. Is that if you have assume that G is finite, so this is the complete opposite of being connected. And that then if you have only one F conjugacy class, if you have only one F conjugacy class on G, this is equivalent to say that the Lang map L is surjective. So this is just a rephrasing of this. But since we are working with finite sets, this means that L is also bijective, is also injective. But meaning that L is injective, this means that the stabilizer of one for this F action is trivial. But the stabilizer of one, we have seen that it is a finite group GF. So this is equivalent to say that G to the F is equal to 1. And in fact, for finite group, admitting an automorphism which with no fixed point, except of course the identity, this is very rare. In fact, if you try to build some automorphism like this, it's quite difficult. And in fact, you can't obtain automorphism in general. In fact, this implies, and this is a theorem by Thomson, that G is nilpotent. Or if you prefer, that it is isomorphic to the direct product of its Sylow subgroups. Okay, so only nilpotent finite groups can admit automorphism without fixed points. This is a theorem by Thomson, the same Thomson as Veit Thomson, and so Thomson gets the Fields Medal. So not only for the Veit Thomson theorem, but also for this kind of results and for the ideas he developed for proving this kind of results. Okay, but as I have said, this is not important for our purpose. So are there questions on FQ structure and Lang theorem at this stage? No question? Okay, so let's go on. Let's go on with some other consequences. And the first consequence will be about action on the group on varieties. So let X be a variety and F, and not always F, almost always F, my Frobenius endomorphism. Let F from X to X be a Frobenius endomorphism. So I assume that X is defined over FQ. Okay. And I assume also that G acts on X, but it acts on X in a way which is compatible with the FQ structure. So we say that, and that this action is defined over FQ. So defined over FQ, this means that if you compute the image under the Frobenius endomorphism of G dot X, okay, this is just the action on X. This is the action of f of g on f of x. Okay. And the proposition that will follow from Lang's theorem is the following: is that if you have an f-stable G orbit, and of course we have to assume that G is collected. Okay, then in fact the fact that the orbit is f-stable implies that there is an f-stable point in it. This is not obvious. Okay, so there is an f-stable point in the orbit. I recall that an orbit is always a locally closed subvariety. So this is a variety, but this is a variety with FQ rational point. And the second result is that if I fix such an element, and so an f-stable element in my orbit, then the map that goes from, so I start from OF, okay? But an element in OF, since O is an orbit, this is obtained as the action of an element of G on X0, okay? But for the moment, I don't know if G is f-stable, and I want to associate to this the F class of G minus 1 f of G. And in which set do I go? I go, in fact, to the set of F conjugacy classes in the stabilizer of X0. And as I have said in the previous result, the corollary 6.2, the F conjugacy classes in the stabilizer, this is the same as the F conjugacy classes in this finite quotient. And when I get such a map, okay, in fact, it is well defined if I take G orbit, GF orbit. So it sends the GF orbit of Gx0 to the F class of G minus 1 f of G. And so this map is well defined. And bijective. Okay. So in fact, so this proposition tells you how the fixed point, first tells you that the fixed point under F in this orbit is non-empty, but also it gives you a way to parameterize the GF orbits inside the set of fixed point. Okay, this set of fixed point is acted on by GF, and it's, in general, there are more than only one orbit, and they are parameterized by this finite set. So let's prove this result, and you will see how we use the Lang's theorem. Okay. So let X be an element in the orbit. Okay. Then, since the orbit is f-stable, it means that there exists G in G, such that if I apply f to X, it will remain in the same orbit, so it is equal to G times to G applied to F. But by Lang's theorem, we can write G, so let's say G inverse as A minus 1 f of A. Okay, and then you can check that if you compute f of A dot X, this is equal to f of A dot f of X. But f of A, this is equal to A times G inverse. by the above equality, and f of x, this is equal to g dot x. And at the end, you get a dot x. And so this proves that a dot x is an element which is fixed under the Frobenius endomorphism. So this is really a direct application of Lang's theorem. Okay, let's talk about the second result. So first of all, so I have decided to define a map that sends the g orbit of this guy to this guy. So first of all, I must, to see that it is well defined, I must check that g minus 1 f inverse belongs to the stabilizer. Okay. But not only I must prove that it belongs to the stabilizer, I must also prove that it is well defined, because there are several ways to write gx0, to write an element as the action of g on x0, of little g. You can take another g prime, and you see it. We should prove that it does not depend on the representative in the GF orbit. So that's what we need to prove. So first of all, if g dot x0 is equal to g dot x0, then this is very easy to check that this is equivalent to say that g minus 1 f of g stabilizes x0. Okay, this is just a translation, because you must use that f of x0 is equal to x0. Now, if gx0 is equal to hx0, okay, then the element u, which is equal to g minus 1 h, it belongs to the stabilizer of x0. And moreover, if you compute g minus 1 f of g, you obtain that this is g minus 1 h times h minus 1 f of h times f of h minus 1 g. Okay, but g minus 1 h, this is u. Here, this is h minus 1 f of h. And f of this guy is just f of u inverse. So you see that these two elements, this one and this one, are f conjugate inside g of x0, because u belongs to gx0. So, and I write it like this: g minus 1 f of g is f conjugate to h minus 1 f of h in gx0. So you see that first, the map does not depend on the way you write you write your elements. If you take two different g and h, such as gx0 is equal to h0, you obtain at the end the same f conjugacy class. And now, if alpha is an element of GF, then through this map, then you can check that if you compute alpha g inverse f of alpha g, then this is equal to g minus 1 f of g. Okay. So in particular, alpha gx0 and gx0 have the same image. Under this map. Okay. So this was to prove. So this proves that the map is well defined. In fact, that's the hardest part. When you know that it is well defined, proving the bijectivity is easy, and I leave it as an exercise. And that's a good exercise to train to use Lang's theorem. Okay, so that's the first consequence. A second consequence is that we can use this result to have some flexibility, and this can be useful to have some flexibility. I explain what I mean by flexibility. So I fix an element G in G0, so in the connected component, and I want to say that the following result, then the pairs G endowed with the Frobenius F and G endowed with the Frobenius GF. I recall that GF is the Frobenius which is twisted by G. This is this guy here. In fact, these two pairs are in fact isomorphic. So what do I mean by isomorphic? I mean that there is an isomorphism from G to G, that sends the Frobenius F to the Frobenius GF. And how is it constructed? It's fairly easy, again, using Lang's theorem. For this, write G as A minus 1 F of A. This is again Lang's theorem, okay? And write, I denote by F prime the Frobenius endomorphism GF. Then the map that I denote by CA, which is the conjugacy by A, that goes from G to G, that sends an element H to its conjugate by A. So this is an inner automorphism of the group G, okay? And but this map satisfies that if you compute CA of F prime of H, okay, this is F of CA of H. So this map transports the Frobenius F prime to the Frobenius F. And in particular, you get that the finite group defined by GF is isomorphic to the finite group defined by F. So twisting the Frobenius by the element G does not change fundamentally your finite group. This automorphism is obtained by the conjugacy by CA, but you must be very careful here. Really, you need that G belongs to G0, okay? This is false in general if you don't assume that G belongs to G0, okay? If you twist by an element which is not in G0, then you change the FQ structure. You really change the FQ structure, and you can obtain a very different algebra, a very different finite group at the end. But if you twist by an element which belongs to G0, then in fact you don't change up to isomorphism the finite group you will be interested in. Okay, and that might be very useful. Okay, so let me give some other examples of applications of this Lang's theorem. So this is example 6.4. So if H is an F-stable connected closed subgroup of G. Then, if you want to compute the F-stable classes modulo H, okay, the F-stable classes, then in fact, so since H is connected, we are interested in the action of H on by right multiplication on G. H is connected, so each F-stable classes admits a fixed point, so you obtain at least a quotient of GF, but this is a quotient by HF because each orbit, in this case, each orbit, the stabilizer of a point in each orbit is trivial, so the group of F conjugacy class of the trivial group is trivial, and by Lang's theorem, this implies that you have such a bijection. Maybe I should write a natural bijection instead of an equality, but I will always often write equalities in this case. Okay, so here it's very important that H is connected. Okay, it's very important that H is connected, but you don't require, and that's also important, you don't require that J is connected. What is important is that the group which acts, and that's the group H, you just require that the group which acts is connected. And I conclude this application, but there will be some others, by talking about Galois ramified covering. Because in fact, my Lang map is a non-ramified covering. In fact, the Lang map L from G to G is an orbit map for the left is an orbit map for the action of GF on G by left translation. Indeed, L of G equal L of H. This is equivalent to say that, so I must be careful, G minus 1 to G minus 1 H belongs to GF. And of course, this is not this is G H inverse. Okay, belongs to GF. Okay, so this is an orbit map, but also, if you compute the differential of the Lang map at the neutral element, this is a map that goes from the tangent space at one of G. This is, of course, often called the Lie algebra of G. And this map, in fact, it sends an element X to, so L, this is G minus 1 F of G. So taking the inverse, the derivative will give you the opposite. And the derivative of the Frobenius is, we have seen that it is always 0. Okay, so in fact, the differential is just taking the opposite. So this implies that it was thanks to proposition 4.5. Okay, this implies that as a variety, if you take the quotient, so I write it like this, of G by the left action of GF, this is isomorphic as a variety through the factorization of the Lang map to G itself. So you take you have a quotient of G by a subgroup, which is isomorphic as a variety to G. Quite funny, isn't it? Okay, and since G acts freely, since GF Ax3. This is left translation. This is a Galois and ramified covering. So at this stage, I must say that sometimes we are talking about simply connected groups. For instance, we say that SLN is simply connected. But simply connected in our head, this means that there is no unramified covering. In fact, this is not true in characteristic P. Being simply connected means only that there is no tame ramified covering. That means that there is no covering by groups of order prime to P. Okay, that's the same thing as that happens with a affine line. You remember that there is no Galois unramified covering of the affine line in characteristic P by P prime groups, but there are many covering by groups of order divisible by P. And here you see an example where, for instance, of where SLNF, this we think SLNF as something which is simply connected, but it for the in characteristic P, it is not simply connected. It has many different coverings. Okay. Okay. So are there other questions at this stage about these applications of the Lang map? So really, this application, the proposition 6.3, is really is very important. Okay, and we will see immediately some how it can be used. But so if you have questions, don't hesitate. There are no questions? Okay, so let's go on with the objects that the dual-linguistic theory wants to study representations. So this is the class of finite reductive groups. Or finite groups of Lie type. So at the first glance, you must think that it is quite a strange terminology, and it is a strange terminology to say finite reductive group, because a finite group is reductive always. Okay, so you can wonder why we had the term reductive, but this is quite an ambiguous terminology. It means that it is a finite group which is obtained by the group of FQ rational points of a connected reductive algebraic group. So that's what I'm going to say now. So let G be a connected reductive group endowed with a Frobenius endomorphism. F over FQ. Okay. And you remember that if you are not comfortable with connected reductive group, as I have said, think G is equal to GLN. Okay, that will be enough. And if you want, you can take F to be the very natural Frobenius endomorphism. Okay. So now I take B prime to be a Borel subgroup. So I recall that for understanding the structure of reductive groups, there are many subgroups that are interesting. There are the Borel subgroups, there are the maximal tori. There is also the Weil group, which is the normalizer of the maximal tori over the maximal tori. Inside the Weil group, there is a special set of generators. All these guys are defined over an algebraic closure. And the importance of Lang theorem is that it will show you that you can choose all these objects to be F-stable so that the structure of the finite reductive group you obtain will really reflect the structure of the full reductive group over the algebraic closure. So first of all, we need to prove that there is an F-stable Borel subgroup. And this works thanks to the proposition 6.3. So because the set of Borel subgroups is in bijection with, since all the Borel subgroups are conjugate, so I shouldn't put 2 bar, only 1 bar is sufficient. Okay. Since all the Borel subgroups are conjugate, this is in bijection with G modulo the normalizer in G of B prime. But the normalizer of G on B prime is equal to B prime. So this was the theorem 520, I think, in the last lecture. Okay. So this is because all Borel subgroups are conjugate because the normalizer of the Borel subgroup is equal to itself. Okay. And in particular, so this is equal to G mod B prime, and F of a Borel subgroup, and F of a Borel subgroup is a Borel subgroup. Okay, because what is a Borel subgroup? This is a maximal connected solvable group, and all these properties are stabilized by F because F is a morphism of variety which is bijective on points. Okay, so this sends a connecting group on a connected group, a solvable one on a solvable one, and the maximal one on the maximal one. For otherwise, the dimension will be there will be a problem with the dimension. Okay, so in particular, this means that the variety. So we can endow the set of Borel subgroups with a structure of variety, and this variety is endowed with the Frobenius endomorphism. So the variety of Borel subgroups and that's what we call the flag variety in the last lecture is defined over FQ. Okay, but now G acts transitively on this variety. So the variety is a single orbit. So since it is a single orbit, the proposition 6.3 and the first statement of proposition 6.3 implies that there exists an F-stable Borel subgroup. And that I denote by B0. Okay. Okay. So that's an argument that we have done for Borel subgroups. So we have proved that all the Borel subgroups, well, there exists an F-stable Borel subgroup. But what we have used is that we have just used that all the Borel subgroups are conjugate. That's the only fact we have used. But there is another class of groups for which this works. This is the class of maximal tori. So the maximal tori inside B0 are also all conjugate inside B0. And so in particular, we can apply the same argument to see that there exists an F-stable maximal torus. That I denote by T0 inside B0. Okay, so in particular, an exercise an exercise is that the pair T0, B0 is unique up to conjugacy under the action of GF. So not only we have such a pair, but it is essentially unique as long as we are interested in our F-stable guy. So now I have my my pair TB. I can define the Weil group. Again, in GLN, this is just SN, sorry, the symmetric group SN. And I can define the special set of generator, S. This is a set of elements in W, such as the dimension of BSB minus the dimension of B is equal to 1. Okay. And you see that since T0 and B0 are F-stable, the group W will admit an action of F, and this action will stabilize the set S because everything is defined intrinsically in terms of, and I must say B0, B0, and B0 here, okay, to be coherent. So finally, what can I deduce from Lang's? This is again application of Lang's theorem, is that I have an F-stable Borel subgroup B0. I have an F-stable maximal torus inside B0. I have my Weil group and I have a set S, and the group W is acted on by F, and moreover, here, the particular set of generators is stable under the action of F. Okay? And we can see an immediate application of this. So first of all, if W is a fixed point under the action of F in W, I choose a representative W dot of W in the normalizer in G of T0 F. Because why can I choose an F-stable representative? This is because T0 is connected, and I apply just the example 6.4. The example 6.4 is this one that says that an F-stable class admits always an F-stable representative if I take the quotient by a connected subgroup. And in this case, the connected subgroup, this is just T0. But it must be said that the group NG of T0 is far from being connected. Okay. Okay, but what is important is that this guy is connected. Okay. So now I can prove a finite Breuer decomposition. Oh, I must state what it is. So finite Breuer decomposition tells you that you can obtain the decomposition of GF into double classes, the disjoint union for W in WF of B0F W dot B0F. And the proof is fairly easy. Okay, so the fact that the union is disjoint follows from the fact that it is disjoint in the full group. But what is important is that we must prove that an element in GF belongs to this union of classes. Okay, so since it is an element in G of G, the Brugha decomposition tells you that there exists W in W such that G belongs to B0 W B0. So this is here the infinite group. Okay, but f of G is equal to G, so it belongs to f of B0 W dot B0, which is equal to B0 f of W dot B0. Okay, this is because B0 is F-stable, so this is the advantage of having taken as our basis for understanding the structure of G and F-stable Borel subgroup. And you see that in this case, this implies in particular that since G belongs to this double class and this double class, well, the Brugha decomposition tells you that f of W is equal to W. This is by Brugha decomposition for G. So this is the theorem 524b. Okay. Okay. So in particular, this implies that W is in WF. But now, why? So in particular, its representative is in WF. But why can we choose G to belong to be in the orbit of B0F cross B0F? And in fact, if I denote by O of W, this is the orbit of W dot under the action of B0. So this is an F-stable B0 cross B0 orbit. Okay, for left and right translation, the first copy of B0 acts by left translation, the second copy acts by right translation. So in particular, you have that the set of double classes inside OWF modulo B0F. Okay, this is in bijection. This is by proposition 6.3. Bijection with H1 of F times the stabilizer H1 of F with values in the stabilizer of W dot. So the stabilizer of W dot in B0 cross B0, but it is easy to check that the stabilizer is isomorphic to B0 intersected with W dot times B0, the conjugate of B0 by W dot. So this is proposition 6.3 that tells you that you have this bijection. Your element G belongs to this guy, and it's a fact that's not difficult, but not easy. It's not difficult and not easy. This is the fact that this guy is connected. And for this, you need to go further into the structure of reductive groups, for instance, to use root systems. Okay, so this is connected. So this guy has only one element. Okay, so this means that there is only one B0 cross B0F cross B0F orbit in OW dot of F. And since G belongs to this guy, this implies our result. Okay. So this concludes the proof of the finite Brugha decomposition, which can be deduced thanks to Lang's theorem, applied many times to the Brugha decomposition for the infinite group. Okay. Let me give some example. Let me give some example. So, of course, as usual, my example will be to take G to be G, and I will denote by Gn, okay, to be GLN of F. And I take F to be the natural Frobenius endomorphism that sends a matrix to the same matrix with entries where entries are raised to the q's power. Okay. And then we must choose inside this group. We must find the theory tells you that you can find an F-stable Borel subgroup. Well, in fact, in this case, this is easy. You can take B0 to be the group of upper triangular matrices. Then it is F-stable. Okay. And you can take T0 to be the group of diagonal matrices. It is also F-stable. Okay. So this is easy to have to find an F-stable Borel subgroup and an F-stable maximal torus. But it is much less easy for the twisted Frobenius, the one that defines the unitary group. Recall that I define Fu, U for unitary, that sends a matrix Aij to the same matrix Aij, but raising the power, the entries to the q's power and taking the transpose of the inverse. Then in this case, the maximal torus is Fu stable, okay, but Bn is not. Okay, it is not because if you apply this twisted Frobenius to the upper triangular matrices, taking the transpose of the inverse, we send an upper triangular matrix to a lower triangular matrix. So our favorite Borel group is not stable under the action of this Frobenius. And this is really a problem for understanding the structure of the unitary group. And in fact, it is very difficult to find an Fu stable Borel subgroup for this Fu. But we will use the flexibility, okay? And so using the flexibility, what I call the flexibility, okay? We let, so I denote by W0 to be the matrix with ones on the anti-diagonal and 0 everywhere else. So this is an element of my general linear group Gn, which is connected. Okay, so we can replace Fu by F prime which is just a composition of Fu by the conjugacy by W0. the flexibility tells you that if you are just interested in the finite reductive group, the underlying finite reductive group, there is no problem in twisting your Frobenius by an element which belongs to the connected component. And that's what we do here. So in this case, we have that Gn f prime is isomorphic to Gn fu, to the unitary group. So this is a different kind of unitary. It just means if you think in terms of the complex number, it means that you have just changed your scalar product in some sense, okay? But that's not a problem. This doesn't change at the end the group you are interested in. And in this case, since I have added this conjugacy by this W0, which is the anti-diagonal, then not only Tn is f prime stable, but Bn and Tn are f prime stable. So for understanding the structure of unitary group, it's really easier, much easier to twist the Frobenius by this action of W0. Okay, and in particular, you can check that what happens for the action on the Weyl group. F acts, so the Weyl group representatives are given by permutation matrices. Permutation matrices are stable under the action of F, so F acts trivially on the Weyl group, which is isomorphic to the symmetric group. Okay, but F prime does not act trivially. It acts on W by conjugacy by W0. Okay, this is easily checked. And what happens, for instance, for the elements in my favorite set of generators, if you conjugate the generator Si by W0 inverse, by W0, so Si, I recall that this is the transposition I plus 1, you obtain the transposition Sn minus I. Okay. Okay, so this example is very important because it tells you that first, theoretically, it's easy to see that there are F-stable Borel subgroup, F-stable maximal tau I, and so on. But when you want to do concrete computations, you must find such a guy. And sometimes finding such a guy can be very difficult. And it is very convenient to have the opportunity to use flexibility to retrieve our favorite guy, in this case, for instance, Bn and Tn to be the upper triangular matrices and the diagonal matrices. Are there some questions? No question? Okay. So I conclude with by talking about F-stable parabolic subgroup. Okay, and that again, now we are used to this kind of arguments. You have a set of representative of parabolic subgroups by the conjugacy class of F-stable parabolic subgroups using subset of I. So I recall that if I is contained in S, then Pi is equal to the union for W in Wi of B0, W B0, and Wi. This is a subgroup generated by I. Okay, then Pi is a parabolic subgroup. and it is F-stable if and only if the subset I is stable under the action of F. For instance, in the case of the general linear group, every subsets are stable under the action of the Frobenius because the Frobenius acts trivially. However, in the case of the unitary group, this is a non-trivial condition. In particular, it tells you that the subset of S you take is in some sense symmetric for this symmetry that exchange I and n minus I. Okay. So there are cases where this is an empty condition, but there are cases where it is an important condition. And the proposition that I want to state without proof, but the proof follows the same lines as before. It uses many times the Lange-Steinberg theorem. This tells you that the set Pi, where I contains S and is F stable, is a set of representatives of GF conjugacy classes of F stable parabolic subgroups. Okay, and again, for all these results, again, just think about GLN. But even if you want to stick to GLN, there is, in some sense, a kind of trivial Frobenius, natural one, but the twisted one that gives a unitary group is an interesting one. And I encourage you to see what this means in the unitary group. So I have finished this chapter. I will start the next one on Harish-Chandra theory. It will be just a start, okay? But before starting the next chapter, of course, if you have questions, that's the moment. Are there questions? No question? Okay, so let's start the chapter 7 on Harish-Chandra theory. Well, in fact, and in this chapter, we fix a connected reductive group G endowed with a Frobenius endomorphism over FQ. Okay, so the Harish-Chandra theory is a theory for starting to study algebraically the representation of the finite group GF. And for this, we need to define some Harish-Chandra induction and Harish-Chandra restriction, as we did for SL2. So Harish-Chandra induction and restriction. So for this, I start with an F-stable parabolic subgroup. So proposition 6.6 just on the left tells you how to obtain representatives of these guys. So let P be an F-stable parabolic subgroup. So if I have an F-stable parabolic subgroup, again, by applying all the arguments we have used before, this implies that P contains an F-stable maximal torus. And this implies that the unique Levy subgroup, the unique Levy complement containing, so this torus I call it T, so, and the unique Levy complement of P containing T is F-stable. Okay, so write, and I denote it by L, this unique Levy complement. I write V to be the unipotent radical of P. Okay, so that we have that P is the semi-direct product of L with V. And taking fixed point, this implies that PF is equal to the semi-direct product of LF with VF. And in particular, the following subspace, the following finite set, the finite set GF mod VF, this finite set is endowed with the left action of GF and with the right action of LF. And in particular, this permutation module becomes a KGF KLF bimodule. Okay, and as we see in the case of SL2, its dual is the dual of this guy is isomorphic to the set of classes in the either direction as a KLF KGF bimodule. Okay, so I can repeat this because I'm changing of page and it's not very okay, so I just recall all of this. So since I have bimodules, okay, since I have a bimodule, I can define functors that I will be named the Harish-Chandra induction and Harish-Chandra restriction. So we can define R L containing P G. So I must use all this notation. This goes from the category of LF bimodule, LF module to the category of GF modules. And it sends a module to the tensor product with this bimodule over KLF. Okay, and in fact, as in the case of SL2, you can also write it as just a classical induction from PF to GF of M tilde, where M tilde is the same guy as M, but we view it as a PF module by letting VF acts trivially on this guy. So we can view M as a PF module by letting VF act trivially. We denote it by M tilde and take the induction. And this is the Harish-Chandra induction. And of course, you have an Harish-Chandra restriction, which is adjoint to this guy. That goes from the category of KGF modules to the category of KLF modules. In that sense, a module M to the tensor product with the other guy, the dual. And again, as in the case of SL2, it can be proved that this is isomorphic to the fixed point of VF, of this finite group VF, for the action on M. Since LF normalizes VF, the fixed point under VF becomes a KLF module, and this is the Harish-Chandra restriction. Okay, so I'm going to conclude with this today's lecture with a proposition which can be called the transitivity of Harish-Chandra induction and restriction. And we will really enter into the Harish-Chandra theory during the next lecture. So how does the transitivity works? Okay, how does it work? So let P be an F-stable parabolic subgroup. No, sorry. Let P prime be an F-stable parabolic subgroup of L. Okay, so I already have an F-stable parabolic subgroup. This is P. I have inside the Levy complement L, but I recall that L, the Levy complement, is also a reductive group. So in some sense, here, this is the functors between categories of representations of objects which are of the same kind. Okay, here you have the finite reductive group defined with G. Here you have a finite reductive group defined with L. And you see that Harish-Chandra induction and restriction will allow to do some kind of induction on the size of the reductive group. So since L is also a reductive group, then it admits also parabolic, Borel, blah, 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 and so on. And so I start with an F-stable parabolic subgroup of L, and it admits again an F-stable Levy complement. Let L prime be an F-stable Levy complement. Then we set V prime to be the unipotent radical of P prime. And the first result here is that if you consider, so P prime is a subgroup of L, so you can consider the semi-direct product of P prime with V, okay? P prime is a subgroup of L, so it acts on V. You can take the semi-direct product. And in fact, this guy, this is a parabolic subgroup, is an F-stable subgroup of G, of the big group, with Levy complement L prime and unipotent radical L prime. Okay, and in fact, this fact allows me to at least to state the result, and the result is that there is some transitivity. If you do Harish-Chandra induction first from L prime to L using the parabolic P prime, and then you compose with Harish-Chandra induction from L to G, it's the same thing as if you do Harish-Chandra induction in only one step, starting from your Levy subgroup L prime contained in the parabolic subgroup P prime times V, which is an F-stable parabolic subgroup, and you Harish-Chandra induce to G. And of course, by adjunction, you have the same result for Harish-Chandra restriction. So here you first restrict from G to L, then you restrict from L to L prime using the parabolic P prime, and you obtain that this is the Harish-Chandra restriction for L prime contained in P prime V G. Okay? And the proof is fairly easy.
I think for part A, there is a typo in the phrase. The unipotent radical should be.
Unipotent, okay. The unipotent radical is V prime V. Yes, thanks. Yes. Well, V prime semi-direct V. Yes, thank you. And you will see immediately this typo appear in the proof, okay? Because this is just saying that the map that goes from GF modulo VF tensored over KLF to KLF modulo V prime F. So here, this bimodule defines the Harish-Chandra restriction, this Harish-Chandra induction. This bimodule defines this Harish-Chandra induction. The tensor product defines the composition, and you must check that it is isomorphic to the bimodule KGF modulo VF times, V prime F times VF, and the map is obvious. You send the class modulo VF tensor the class modulo V prime F just to the product, and this L normalizes V. This is the map that sends this to this, and this is an isomorphism, and this is very easy to check. Okay, so at this stage, you must, I did not prove A. So A is a general result about reductive group, but I would just want to illustrate it in the case of GLN, and this I will conclude. I will just conclude on this. So in the case of GLN, a parabolic subgroup is just the datum of. You can have as an image of a parabolic subgroup a group which is upper triangular by block. So this is the upper triangular bar block, and the part V. This is the unipotent radical is obtained by taking just identity matrix on each block, and random elements above the block diagonal. Okay, so this is a parabolic subgroup G, and VP, sorry, and L is given just by the diagonal block. That's what I have written with L. Now I take a parabolic subgroup. I take a parabolic subgroup of L, but L, this is the same kind of G. This is a product. This is a product of GLN. So, and taking a parabolic subgroup means taking, again, upper triangular matrices by block inside each of the blocks. So for instance, I can take this. That's an example, okay? And what is V prime? V prime, this is this part with identity on the diagonal. V prime, this is this part. Here you have nothing, okay? Here you have V prime, okay? And you see that, and what is L prime? L prime, this is the green guy. Okay, L prime, you see the green guy. And you see that if you multiply V prime by V, then you will obtain the following group. So this is V prime V. Okay, this is this guy, okay? And so you see on this picture that the first statement of the proposition is just trivial, okay? This is not very difficult once you know a little bit of theory of reductive groups. In the case of GLN, this is fairly easy to check. And from this, this means that the transitivity of Harishchandra induction and restriction has a meaning, and not only it has a meaning, but it is true, okay? And this is my conclusion, and we will continue Harishchandra theory in the next lecture. Okay, I stop here. And of course, feel free to ask questions. Yes? Yes, other questions? There are no questions? Okay. If so, maybe we can stop here and see you on Friday. Maybe you will have some. Yes. Sorry.
Just saying yes and great. Thank you.
Okay. Thank you, Peng. Okay. Thank you. See you on Friday.
See you on Friday.
Bye.